Good morning. We will continue the forward flight by introducing the idea of rotor upwash. If you remember, the Glauer's theory, it was an extension of the actuator disk theory to the forward flight and assumed that the velocity down in the wake is also twice the induced velocity at the level of the rotor and the wake is contracting. The Glauer formula we have deduced it in forward flight. However, we did not discuss about the rotor upwash. The idea is that the rotor produces not only downwash but also an upwash, where in forward flight along the leading edge of the disk. You see that it is exactly like in a case of a wing. In a wing, we also have a bound vortex in front of the wing and we have an upwash. So the circulation, which is proportional with the ratio of lift divided by the forward speed, shows that if the velocity decreases, we have a stronger circulation in order to produce the same lift. This happens as well in helicopters. The front area of the disc has an upwash. This is the area of the upwash when we are flying 60 knots, and you see the area of the upwash when we are flying 120 knots. So it is a much larger area, and this is responsible for the upwash. The problems caused by the upwash are as follows. An upwash affects the lateral cyclic pitch which is required to control the rotor flapping. Here you see, for example, the so-called lateral trim phenomenon. You see the forward speed and the lateral cyclic in percentages from full left cyclic to full right cyclic. Here you see the lateral cyclic when we are using a model of 6 degrees of freedom, and you see the lateral trim phenomenon. If the induced velocity in the front of the disk is smaller than induced velocity in the rear of the disk, this is due to the upwash, the angle of attack in the front is increasing. So we are having more lift in front. Therefore, due to the gyroscopic effects, the blade will want to flap up 90 degrees later on the retreating side, and we will have a rolling moment. The pilot explains this lateral flapping as a transverse flow, is like a side wind, and therefore to trim the pilot must use a left stick in order to keep the helicopter rolling to the right. You see as well in this graph that when we are flying at speeds between 20 and 40 knots, we have this extra lateral trim, lateral cyclic that we need in order to not roll to the right. At high speeds, the effect of this upwash is taken over by the coning angle, so the total flapping of the wings. Another problem caused by the upwash is that it affects the lateral cyclic, and this was also observed in the Sikorsky advanced blade concept and the experimental rotor installed on the Kaman UH-2, where the pilot did not have enough lateral stick. Another problem caused by the upwash is the transition vibration. The upwash gives vibration problems when we are going from hover to forward flight. What is happening? The upwash in from, it will send vortices not down but up. Further back they will come down in the rotor, and when the blade will strike these little vortices, it will find a large change in angle of attack and then will create transient vibration. When we are decelerating from forward flight to hover, this transient transition vibration is even worse. Another problem caused by the upwash is the vortex interference problems when the helicopter is flying at high speed. As we said at the twisting for hover, due to twist, the advancing tip is working at negative angles of attack. Therefore, a double vortex system is creating, and this will create large variation in angle of attack, large variation in lift, and therefore vibratory problem. So we see here again that whatever helps hover, it will hurt the forward flight and the high speed, and the other way around. In this way, the helicopter designer has to do a compromise. Another kind of upwash is the so-called pitch side slip coupling. What is this pitch side slip coupling? You see that not only the upwash creates problem, but also the reverse flow region situated in the disc is creating problem. When? When the helicopter is side slipped to the left, so the wind is coming to the pilot from the left, it is that actually we need more stabilizer, and more stabilizer it is in the weak downwash. Therefore, the stabilizer download will decrease as compared to the non-slipping flight, and we will have a nose down moment that the pilot must compensate with aft stick. In this figure you see on the left hand side a helicopter with no side slip, and on the right hand side the left side slip. You see that the reverse flow region affects the stabilizer. This phenomenon was first observed in the Apache, and that produced some accidents. For example, a jacket which instead going down was lifted up by the main rotor, and then it entered into the tail rotor. This ends the definition and the problems introduced by the upwash in forward flight.